In this video I will explain what Kirchhoff's first law is about and how you can use it to calculate the value of resistors which are connected in parallel. And also I will show you an experiment to demonstrate how the current in a network is divided into 3 parallel branches, and also why the total resistance is lower than the individual resistances, and also lastly why the voltage across all branches is the same. My name is Andreas from The Fearless Engineer, and here we go. Now in the previous videos we have only looked at single components each time, and basically what we did was to connect single resistors to different voltage sources and also conduct measurements based on current and voltage and power and also on resistance. And now we will connect several components in a circuit with each other at once, such that current and voltage are spread across these components. And there are 2 elementary rules in electronics for this, which are named after their discoverer, a German physicist called Kirchhoff or Kirchhoff, and in this video we want to look in detail at Kirchhoff's first rule, which describes basically what happens when we split electrical circuits into multiple branches. Now let's start with a short experiment here. And for our circuit we need a voltage source, a multimeter and 3 resistors. And the assembly with a wooden board, which you can see here, is perhaps not suitable for mass production, but it allows us to connect the components among each other and with each other very quickly, and nothing remains hidden which might happen in the background and which you couldn't see. So this is why I chose the setup here. And I also will be able to connect the multimeter very fast and without much effort anywhere in the circuit. And in later videos I will use such a breadboard, which you can see here, for circuit setups. This is basically the standard way for most experimental setups in electronics. But in the videos about Kirchhoff and the current and voltage divider, which are coming up next, I will use the wooden board you can see here for better clarity. And the task of this circuit here is to connect the resistors to the voltage source in such a way that the current branches in front of the resistor and again reunites behind the resistors. And we want to find out by means of measuring according to which rules this splitting and merging happens in the circuit. And 2 of the most important questions will be: 1, how the current is split between the 3 branches, and secondly, 2, how much voltage drops across the resistors. So let's get started here. And first we connect one terminal of the voltage source to the upper nail, which you can see here. And then we take such a crocodile clip and connect the positive terminal to the left resistor. And then we do the same with the middle one, and then after that with the right resistor. And now we have split the current flow into 3 branches, but of course in order to have a closed circuit we need to connect the resistors on the other side to the voltage source as well. And to do this we also take 3 crocodile clips and use them to combine the current flow into one singular point again. And by the way, such points here are also called nodes, and a connection between 2 nodes is called a branch. And we have now created 3 distinct branches, each with a resistor between the upper and the lower node. And finally we have to connect the lower nail to the other terminal of the voltage source, and in doing so we have created a closed circuit with 3 resistors connected in parallel. And now we have to install the current meter to measure the total current flowing through the circuit. And to do this we simply remove the upper lead leading to the voltage source and connect one measuring lead of the amp meter to the nail and the other directly to the positive terminal of the source. And when we activate the circuit in a few moments, the current will flow through the meter and is then divided among the resistors. Now, the voltage source is set to a value of 10 volts and limits the current to a maximum of 100 milliamps so that the circuit components are not damaged. And such a current limitation in this case is very useful because we do not yet know what value the resistors really have, and we also do not know how they behave in a parallel configuration. This is what we're about to find out here. And if you have seen the video about power, you already know what happens when we overdo it with the amount of current through the resistor. And if we switch on the source now, you can see on the display of the meter that there's a total current of 35.82 milliamps flowing from the upper node through the resistor to the lower node and back to the source. But in order to be able to assess this value, it's now time to take a closer look at the individual resistors and to determine their values. And I've already made a video of 3 different ways to do this, and the easiest method would probably be to just pick up your smartphone, enter the color code into an electronics app, but this would be problematic because in this case this would only give you the theoretical value of the resistor, but it doesn't take into account the manufacturing tolerance, which always exists, and this would lead to, of course, to deviations for each individual resistor you pick from the batch. And that's why it's better in this case to measure the actual resistance value directly across the resistor using a multimeter. But to avoid erroneous measurements, we have to first remove the resistors from the circuit, and therefore we now disconnect the upper crocodile clips from the nail. And if you don't know why we have to do this, then please watch my video on how to measure resistors first. The link is coming up now in the cards for you. And now we press the measuring tips to the two connecting legs of the left resistor, and from the display we can see that it has a value of 328 ohms. And for the middle resistor, we do it once more, and the display shows a value of 3267 ohms, which is about 10 times as much as the left resistor. And for the right resistor, the same value as for the middle one is shown, so we also have 3267 ohms here. Now, if you have already seen the video on Ohm's law, then you already know that you can calculate the resistance from voltage and from current, which is exactly what we are going to do here. And to get there, we have to divide the 10 volts of the voltage source by the total current which we have measured. And this is perhaps somewhat surprising to you, because the three resistors we have just measured all have larger individual values. So it seems that the parallel connection of the resistors here causes the total resistance of the circuit to decrease. And that's what we want to examine now much more closely. And we will now measure the current which flows through the resistors one after the other. And for this purpose I have already connected one of the yellow measuring clamps to the upper nail, and now I only have to remove the white crocodile clip at the left resistor so that we do not bypass the measurement. And then we connect the second yellow clamp to the left nail. And if we now switch on the source, we measure a current which flows through the first resistor in a height of 30.02 milliamps, which is almost the total current which flows through the entire circuit, which was just below 36 milliamps. And we do the same again for the middle resistor now, first removing the yellow clamp from the left resistor, then we connect it again so that the total current through the resistor does not change. And then we remove the center clip and connect the measuring probe to the center nail. And if we now switch on the source, we can measure a current of 3.02 milliamps in the middle branch, which is about 10 times less than in the left branch. And in the right branch we do exactly the same thing once again, reconnecting the resistor in the middle, connecting the meter to the right resistor, and then switching on the power source. And we have already found out in the resistance measurement that the middle and the left resistor have the same value, and accordingly the current which we measure here is identical, so also 3.05 milliamps. So what we can already say at first glance is that the current flow through the small resistor is much higher than through the two large resistors, and by about the same factor with which the resistance values differ among each other. Let's have a closer look at the numbers here. If we simply add up the partial currents, we get a value of 36.12 milliamps in total, which is within the accuracy of the meter which we have used, identical to the total current. And thus we can conclude that the total current that flowed into the upper node is identical to the sum of the partial currents flowing through the different branches. And as an equation we could express this observation like this. We sum up the currents in writing I1 plus I2 plus I3 equals I total, which is the sum of all the partial currents that flow out of a node equals the total current that has flowed into the node. And we can also rewrite this equation a little bit by bringing all the currents to one side of the equation, which now would look like I total minus I1 minus I2 minus I3 equals 0. And with this we have already found out Kirchhoff's first rule by conducting a few simple measurements. And this rule states that the sum of all currents for a node must always be 0. And this can also be expressed by a sum which runs from 1 to n, where n is the number of branches connected to a node, over all partial currents ik, and this has to be equal to 0. And we can also express this a little differently by stating that for each node the sum of the incoming currents must be identical to the sum of the outgoing currents. But in order to explain why the total resistance in our circuit is smaller than the individual resistors in it, we need to look at the voltage drop across the resistors as well. We don't have to change anything in the circuit to do this, because voltage is always measured between 2 points during normal operation of the circuit. And the question is always how much potential energy is lost to the charge carriers when they flow through a resistor. And in order to measure the voltage drop across the first resistor, we have to switch the multimeter, which you can see here, to DC voltage, and then press the two measuring probes really firmly onto the nails in front and behind the resistor. And on the display a value slightly below 10 volts is shown for the first resistor, and when we do the same for the middle resistor, pressing the probes onto the nails, and then we also obtain a value slightly below 10 volts, which is the same voltage as for the left resistor, within the accuracy of the measurement. For the right resistor, we do it exactly the same way, and we here also measure a voltage drop of slightly below 10 volts. So we can conclude that if resistors are connected in parallel, the voltage drop is the same for all of them. But why is this the case? And if you have seen the video on current and voltage, you might remember the definition of voltage, which is basically the product of electric field E and distance traveled delta L. So you have a charge carrier and there's a field, and the charge carrier travels a certain distance, a certain length between 2 points, and the distance in between the 2 points is called delta L. And since both the starting point and the end point are the same for all three resistors, namely the node before and the node after, the same amount of potential energy in the electric field is converted into kinetic energy for each charge carrier flowing through one of the resistors. And thus the voltage is a measure for the work performed for each charge carrier as it moves from the lower node to the upper node. And therefore the voltage drop has to be the same across all components which are connected in parallel. And with this knowledge, we can now deduce why the total resistance is smaller in this parallel setup here. And this is how it works. We have already found out that the sum of the currents for a node is 0, which means that I total minus I1 minus I2 minus I3 is identical to 0. And this is according to Kirchhoff's first rule, and also our measurement results support this claim. And when we use Ohm's law to replace the currents in the equation with the expression current equals voltage divided by resistance, we get this equation here, where the difference between all the currents which have been replaced by voltage divided by resistance for total amount, component 1, component 2, component 3, are equal to 0. And since we know that the voltage drop across all resistors is the same, we can also replace the voltage across resistor 1, 2 and 3 with the total voltage, and then we can exclude it from the expression, which delivers us this expression here, which is also identical to 0. And this is why we can divide this expression by the voltage on both sides of the equation, which removes it on the left side. On the right side it's 0 anyhow, and this gives us the three partial resistors which are conveniently assembled on the left side of the equation right next to the total resistance. And if we now bring the three partial resistors to the right side, we get the form 1 divided by total resistance equals 1 divided by R1 minus 1 divided by R2 minus 1 divided by R3. And thus we are able to calculate the total resistance of a parallel circuit from the partial resistance values, which basically gives us this neat equation here. The total resistance is equal to the sum over the inverse of the partial resistors, again after summing them up, inverting it again. And now if we insert the resistor values from our measurements into this equation here, we get this form here. The total resistance is identical to 1 divided by 328 ohms plus 1 divided by 3267 ohms times 2, and then inverting the result, which gives us a total resistance of 373.15 ohms in the end. And this is almost identical to the value of 278.94 ohms, which we have calculated with Ohm's law out of source voltage and out of total current. And the equation for two resistors connected in parallel is simply R1 times R2 divided by R1 plus R2. And if you've seen this equation before, you now know how it can be derived, namely by calculating the equation which we just discussed for the total resistance only for two resistors. And here's one short piece of advice for you. The equation for three resistors is not of the form R1 times R2 times R3 divided by R1 plus R2 plus R3. This is an error which we see very often during exams, and you can try it out for yourself by simply using the formula which we just discussed to bring the different resistors to a common denominator, and it's going to be a little bit longer, the expression which results from this computation. But in case you have numerical values for the resistors, the fastest way probably would be to just add them up as inverse values using your calculator and then invert the result at the end. And now we have shown with measurements and equations what the total value of resistors which are connected in parallel is, but how can we actually explain in terms of physics and actual parameters why more resistors in a circuit cause more current flow? And to understand this, we have to look once more at the equation for the relationship between current and voltage via the material parameters of a resistor. And if you don't know the video on this topic yet, here is the link coming up for you. Now let's take a look at the parameters on the right side one by one and see how the resistors differ. We have already discussed why the voltage drop across the resistors is the same early in the video, so what remains are the material parameters in the right box and the geometric properties of the resistor in the left box. And if we now assume that the resistors are made from the same material, then we can assume that the number of free charge carriers and the charge carrier mobility are also the same. And the elementary charge E is always identical anyway, so what remains are the geometrical properties, which are the cross-sectional area A and the length L. And if we imagine a very simple circuit with only a single resistor, then it's clear that an increase in the cross-sectional area at this resistor leads to more current flow, and an increase in length leads to less current flow. And if we now connect a second identical resistor in parallel, then basically nothing changes with regard to the distance the charge carriers have to travel, because both resistors share the node before and the node after. But what does change, however, is the cross-sectional area, and with that the amount of free charge carriers within the volume of the resistors moved along by the electric field. Because the electrons moving from the first node to the second node, they flow through both branches, and the upper branch contains an area A1, and the lower branch contains an area A2 through which they travel. And you can easily imagine these areas in a combined fashion. So if we connect resistors in parallel, the increasing surface area increases the volume of material, and thus also the amount of free charge carriers which are contained in this material, and thus the current flow. And this means that the total resistance of two individual resistors connected in parallel is proportional to the inverse of the total area, which can be expressed as 1 divided by the sum of both areas. Or if it's 3 resistors, 1 divided by the sum of 3 areas. In this video I've shown you what Kirchhoff's first law is about and how you can use it to determine the value of resistors which are connected in parallel. We have also learned that when resistors are connected in this way, their cross-sectional areas add up, leading to more current flow through a circuit than would have been the case with a single resistor alone. And the reason for this is basically with increasing surface area you increase the volume of the resistor material, and thus the number of free moving charges which can be pushed along by the electric field. So we can say that the total resistance of a set of resistors connected in parallel is smaller than the resistance value of a single resistor. And by the way, Kirchhoff's first law is one of the basic equations in electrical engineering and electronics. And we will look at some more applications of these equations in the future. And this could be, for example, when we do network analysis, or when we deal with the current and voltage divider, which we will discuss in the next few videos. And as always, if you have any questions or requests for topics I should cover here, just write me a comment down below, and maybe I will pick up your idea and make one of the next videos out of it. And if you liked this video here, please consider subscribing to my channel, because this really keeps me motivated to continue producing these videos for you. And finally, one last tip from me: you can download all my learning materials such as slides and circuit simulations and such from my website at the fearlessengineer.com. The link is coming up now in the banner here. And that's it from me for now. Have fun and see you next time here on the Fearless Engineer.